Welcome to our courses of advanced power electronics and control. We are discussing about the cycloconverter. Today we will be continuing to discuss cycloconverter and thereafter matrix converter will be discussed. So, as we have discussed in previous class, cycloconverter is direct frequency as well as the voltage conversion. So, cycloconverter is essentially a direct frequency changer to convert AC power to another frequency, and cycloconverter used for the high power applications in driving synchronous machines or induction machine, this kind of where it is actually it runs in a constant speed at a constant frequency. They are usually phase controlled, they use thyristors because of the high power rating. With the invent of the IGCTs, gradually this technology will evolve and we may see that actually phase out of this technology. So, we have discussed in previous class also, just little recap. So, what is the difference between this dual converter and this? Minded in dual converter, what used to happen essentially is that we have a DC load here, but you will have a AC load, but otherwise it will act in the same manner. So, this converter will be said to be the converter P. Once it will switch on, the positive cycle will be generated, and once it will be switched on, the negative cycle will be generated, and so that you can have a variable frequency as well as a variable RMS value. So, this is the configurations of it. So, you got an AC load and you can have think about it, power can sink this way and it can go out this way. So, and the control will ensure that a different kind of switching pattern. So, if you wish to step down the frequency, you can also step it up, but mostly these are step down for the V/F control and other issues. So, what happen till this time you are switching continuously the converter 1, and thus you get and you can control the magnitude by controlling alpha, and thus you get basically consecutive positive cycles, and fundamental will be this. Similarly, it will be a consecutively negative cycle, fundamental will be this, but mind it, this simplicity arises due to the RL load as for only the normal resistive node. But if you have a RL load and if you assume that actually high current flows, then switching will be little difficult because you have to turn it on when the current through the thyristor is going to be low or 0. So, for this reason you can see that you want to generate this profile, you will be actually switching on this portion of the voltage, alpha should be changed. Thereafter you will decrease the alpha. So, you have a more conduction angle, gradually conduction angle will increase, and thereafter again it will reduce the conduction angle, and thus it will track this envelope. Similarly, it is repeated in negative half cycle, and thus what you will get, this is the output voltage across this AC load, and this is the output current across this AC load for RL or inductive loading. Now, same concept can be actually used for the 3-level half bridge converter. So, you have basically we have already discussed basically half bridge converter. 2 half bridge converter will be actually connected, and thus what will happen. So, if consecutively positive half cycle is triggered, load will get this kind of positive half cycle, then if it is negative half cycle is triggered, load will get a negative half cycle, and all the free phase can be constituted. Here only single line diagram has been shown. So, proper diagram 3 pulse cycloconverter of the 3 phase load should be like this. So, this is for the phase A, phase B, phase C, and this is the thyristors, and this is for the positive part of the voltage of phase A, and this will be the negative part of the voltage for phase A. Similarly, this will be for phase B and phase C and so on, and thus you get a variable voltage and frequency at the 3 phase output. So, you can see that this is for the half bridge configurations or half wave configuration. So, in this case also you require, for each phase you require 6 thyristors, and thus total 8 thyristors is required. But if you wish to have a full bridge, so number of thyristors will be 36. So, thus what will happen, this is the way you will generate. How you will generate? First you will trigger actually the phase A of this voltage, and this portion of the voltage you will get. Thereafter again, depending on the positive sequence you will get this kind of voltage, and gradually you will trigger on, this is for the A, B, C, this is corresponding to the 1, 2, 3, and thus from positive, because till this point phase A have a maximum voltage. After this, basically after 120 degree, phase B will have a positive sequence. So, then voltage will come from the phase B, and that has been marked as 2. Similarly, it will be from phase 3. Similarly, again after 360 degree apart, this phase A will be positive, that is marked as 1, and again it will be triggered, and their alpha will be changed to actually increase the magnitude. So, fundamental will be actually having this kind of pattern. Same thing is repeated, but this is for the inversion operation and this is for the rectification operations. Please understand that here, considering that RL load, till this point voltage is positive, current is negative. So, amount of the energy spent here is essentially negative. Here basically it is a rectification operation. Again at this point voltage become negative and current become positive. So, it will be again a inversion operation. Similarly, when voltage and current both are negative, you have a rectification operation. So, in that way you have to actually generate this. This is an example of the output voltage waveform of a single phase of the 3 phase of 3 pulse cycloconverter operating at 15 hertz from the 50 hertz supply at power factor 0.6 lagging. Of course, you can have a circulating current mode operation. This is something it is interesting to note. So, we have seen that once voltage is positive and current is negative, that is, it is inversion mode. When both voltage and current are positive, it is in a rectifying mode. Now, let us see that it is a p type output converter and it is operating in such a way, this is a rectifying mode, and when n type is operating, so this is the inverting mode for it. When p type converter is generating a positive voltage, we will say that it is a rectifier operation, and p type converter is generating the negative voltage, then we will say that it is a inverting operation. Similarly, a n type converter is generating a positive voltage, we will say that it is an inverting operation, and once the n type converter is generating the negative voltage, we say that it is a rectification. So, output voltage of the load, if you combine these two process, you will get essentially this, and this is the reactor voltage, that is, that will appear across this inductor. So, across this inductors, because there will be a instantaneous voltage difference between this actually positive and the negative converter, and this will be have a pi keys, and thus this will be smoothened by this actually the inductor, and you will have this value of the circulating current, and you have to allow the path to flow this circulating current. That is the one of the greatest challenge of the cycloconverter. So, see that we wanted to basically a stepping down of the frequency, and thus from the 50 hertz you try to get this maybe 15 hertz or something, and desired output is this. So, this is a voltage and this is a current, and it is lagging by some degree. So, what happened initially, since it is an inversion operation, you have a choice. You may use actually the negative converter and you can generate the negative part of it. So, for this reason at this time p type converter is being switched off and whole contribution is coming from the n type converter. So, it is been switched till this point where voltage and current, actually current is crossing 0 and thus become positive. And till this, from this point onward, p type converter will take the lead and ultimately it will conduct till the voltage becomes 0, that means at this point. So, till this point. Then also what you generally do, we do not generally switch it off and generally it will continue to work in an inverting mode. Thereafter, once current also become negative, you switch it on the n type voltage and effectively you will get this load voltage across this actually the reactor. So, this portion is inverting, thereafter rectifying, thereafter inverting, thereafter rectifying. Bind it, after rectification again inversion operation start and thus actually it will continue with the n type converter. So, now you have understood the logic why we are starting with the n type converter, because at this point n type converter was functional. So, this is the realization that require 36 switches. So, of the 3 phase 6 pulse cycloconverter, ultimately voltage becomes half in case of the half wave. So, that much of sacrification cannot be done, and so this is the individual load of 3 phase load and this is a supply and you can generate this actually different kind of frequency and the voltage depending on the requirement. So, same thing, this is a desired voltage and this is output voltage, this operation is an inverting operation and for this reason generally it is followed by the negative half cycle. So, you will be switching on this load voltage in such a manner you will get it. From there will be a transition of rectification mode and similarly it will be converted into the, it is inverting mode, thereafter again it is a rectification mode. So, this is the way we actually operate Cycloconverter, but one of the challenge is that it require huge number of switches. That is one of the biggest challenge of it. Now, another problem is that current has to be given a path, one challenge, because all thyristors are the current controlling device. So, controlling is really difficult and commutation failure anytime may occur. Apart from that, this reactor voltage is basically a spiky in nature and that cause lot of stress on the inductor and also actually causes the EMI EMCs. Now, can we have another type of AC to AC conversion? And another challenge it should have basically we try to mimic the characteristics of the transformer. So, essentially what you want to do, you require to step up and step down. Here you can play with the frequencies, you can increase the frequency, decrease the frequency, but generally voltage are being bucked or reduced. But we can have another type of converter that we will be discussing right now, that is also an AC to AC conversion, and that is one of the modern actually area of research, and also we will see that its efficiency and applications. So, AC to AC conversion, this is the overall actually the positions pictorial representation. We can have a converter with the DC link. That means first you convert AC to DC followed by DC to AC conversion. So, we require a DC link and thereafter we may have a, and thus we require a bulky capacitor, and in between you may actually have a AC to DC or DC to AC followed by a current link. Then we require a bulky inductor, and we may have a hybrid matrix converter, hybrid dielectric matrix converter and hybrid indirect matrix conversion. So, there will be some portion of the DC link. And now we are interested in this part, like we have studied cycloconverter, we like to remove the DC link, and thus we have matrix converter. We can have a direct matrix converter, we can have a indirect matrix converter, and direct matrix converter will have a conventional matrix converter as well as there will be a full bridge matrix converter. Similarly, indirect matrix converter will be there, AC to DC and DC to AC converter with link capacitor, full bridge matrix converter and parts matrix converter, or it is called SMC or VMC or EMC, we will see that, and 3 level matrix converter. So, to cater the need of the higher voltage rating or level is required to increase. So, there we have a chance to actually increase the level by multi-level instead of the 3 level, we can state multi-level matrix converter. Now, what is the utility of the matrix converter? So, these are the few things. Since it is a modern topic, it is not available of the many of the books. So, for this I try to actually simplify this content by saying some introduction. These 2 stages of energy conversion is a popular approach in industrial applications. So, we try to remove the bulky DC link with the capacitor or inductor. Nowadays, in almost all industries, conventional AC DC AC conversion system is used, like DC link capacitor in between, which means the system bulkier and the costly. To avoid this, MC was introduced, which works on the single stage as well as 2 stage topology without DC link capacitor in between. Matrix converter arranges semiconductor switches into a matrix configurations and control them to convert an AC input voltage to the desired AC voltage. So, let us say you have V by F control. So, we require precisions of V by F that can be done by the matrix converter. Since the input AC voltage is not converted into the DC voltage, so energy storing element like DC link, electrolytic capacitor, or if it is a current source, then we require a high inductor, it is no longer required in this case and system become compact. So, matrix converter topologies are basically divided into the direct matrix converter and the indirect matrix converter. In case of the direct matrix converter, there is no intermediate stage. So, it will be direct conversion. The input fixed AC is directly converted into output variable AC. But in case of the indirect matrix converter, first input AC voltage is converted to the DC voltage, and in next stage it is converted to the variable AC voltage. The switches in the indirect matrix converter are controlled in such a way that fictitious DC link is created. We shall discuss in detail how it has been done. It is quite interesting phenomena. Intermediate stage, avoiding use of the DC link capacitor. Now, This is the example of a direct matrix converter, and it is abbreviated as DMC. So, you have 3 phase matrix converter, and mind you that there is also a problem of the circulating current here. So, you want a bidirectional switch. So, because current and voltage can have different kind of phase lag and phase lead, and thus it will conduct. So, for this example, if you consider that between A and B, if VAB is greater than 0 and you have given pulses to both T1 and T2, then path of the current will be this. If VAB is less than 0, then path of the current will be through this. Then what will happen then, if voltage or current has a phase lag? If voltage is positive, current is still negative. Then also, since pulse is been actually continuously given to turn it on, so it will continue to flow in that mode. Then only when current goes to 0, then only it changes the tracks of these 2 points. Essentially, if AB is 0 and current is greater than 0, then definitely path is through T1 D2. But again, if it is still greater than 0, path is still T1 D2. Once actually VAB is less than 0 and IA is less than 0, then you will find that path is 2 basically through will be this, and ultimately in this configuration path will be through T2 D1. So, this is the way it will work. So, we require, but mind it, we have studied inverter and generally we have required an inverter leg. Mostly this has been constituted by IGBT. It has this source, generally what happened in IGBT in normal configuration, source and drain are connected together. This is a source of the upper thyristors and there is a drain of the lower thyristor. This is the configurations of the inverter legs, but here you will have a difference. You will find that actually both the sources are been shorted together. So, to make it a bidirectional switch, we have a many way to constitute a bidirectional switch. It is not the single way. We can take an example of this example. And this switch can be IGBT or MOSFET. So, one of the advantage of this devices is that, so you have only one controlling device, but disadvantage is that you require actually while current flowing actually account the drop across the 4 devices. So, that is something. This is this device, 3 devices, and also while coming it will have a 3 devices, but here it will account the 2 devices, but both require to be a control device. So, you have a choice. If current rating is small, then we sometimes go for this kind of configurations, and let us draw in a little a manner. So, if you wish to actually bidirectional switch with one controlling device, so that can be, this is IGBT or MOSFET. Then and this is the path, let us say A and B. So, this is a path, and if you wish current to flow or the voltage to flow. So, let us name it D1, let us say T, because there is only one controlling devices, and this one is D2, let us say D3, D4. So, if VAB is positive, then through D1, T, D2, and if VAB is negative, it is D3, T, D4. This is the way basically current will flow, and we can realize a bidirectional switch. We require a bidirectional switch to work with the matrix converter. Now, this is the configuration. Now, accordingly you will generate. So, ultimately you require 9 such switches, and look, there is a distinct advantage of this matrix converter over the cycloconverter. Full bridge cycloconverter require 36 switches, and here to constitute these switches you can have a one switch which we have shown, but you will have a 2 diode drop and one switch drop. So, conduction losses will be more. Otherwise, you can realize with the 2 switches. So, one switch and one drop will be there, one diode drop will be there, then number of switches required to be 18. So, you have a choice. So, for this reason, by considering the component count, matrix converter have been edged on the cycloconverter. So, now see that if you wish to generate, if you wish that actually it should be connected, so that you get a higher voltage, so that you want that F has to be connected, you will short it. Similarly, you can have a short, but there is an issue like total time if it is T. So, TA plus TB plus TC should be same, will be equal to basically the switching time. So, we shall see that what is how we can control the switching logic of the matrix converter in our next class. And matrix converter is quite important in the sense that because we can eliminate the DC link and you no longer require a bulky thyristors with the commutation circuit to achieve the direct AC to AC conversion. So, this is actually quite a modern concept and it is evolving, and with the SiC devices like modern devices like silicon carbide devices, we can definitely have a higher rating matrix converter. Thank you for your attention. We shall continue with the matrix converter in our next classes.